Hey everyone, this is the last video lecture of the year. It takes care of section 6.3, deals with solving systems of ordinary differential equations. So just as we solved the system of algebraic equations, many applicable problems in ecology, chemistry, mechanics, or electricity can be modeled by a system of differential equations. Okay, we can also solve higher order ordinary differential equations by decomposing them into a system of first order ODEs. So here, in order to solve these numerically, we just use Euler's method and improved Euler, or the trapezoid method that we saw in the last couple of sections. So here's what a system of ODEs looks like. So we have y prime 1 is equal to some function of t, y1, y2, y3, however many variables we have, depending on however many equations we have. So y prime 2 would be equal to some other function of t, y1, y2, and so on. Through y prime of n, we can have n equations. We would just have to have n variables here. Okay. So in an initial value problem, if we were to look at an initial value problem, we would need initial conditions for every one of those variables, y1, y2, y3, all the way to yn. So let's look at how we do something like that. So here we have, and again, these systems, basically we're looking at how the rates of two different quantities are related to each other, and it can be used to solve lots of pretty neat applications. So let's apply Euler's method with h equal to 1/4 and t on the interval 0 to 1 to approximate the solution at t equals 1 to this first order system. Okay, so we see that we have the system of equations. Y prime 1 is y2 squared minus 2 times y1, and y prime 2, our second function, is equal to y1 minus y2 minus 2 y2 squared. So to use Euler's method here, it's basically just another layer of Euler's method. We're going to apply Euler's method to both equations separately but simultaneously, because you can see that the equations depend on variables in this equation depend on the function, the second function, and variables in the second derivative function depend on the solution from the first equation. We see our initial conditions for each of the variables here. So let's get started with that. So here's example 1. Okay. So what we want to do, basically what we're going to do is Euler's method for, let's say, for equation 1, for the first equation. How would Euler's method look? Well, our approximation that we've been using is the letter W, right? But we need to notate that this is the approximation for the first equation, okay? So the next function value for the first equation would equal the approximation at the previous step, say, I of the first equation, plus h times f of the previous t, the previous approximation for the first equation, and the previous approximation for the second equation. Okay? Because f is a function, can be a function of 3 variables this time: the t's, the approximations from the first equation and the approximations from the second equation. So keep in mind that this subscript here denotes the iteration, and this subscript denotes the equation number. Okay? So you can see that when we do Euler for the first equation, it's going to be dependent upon the previous approximation from the first equation, possibly the previous t value, which are the same, t's are the same in both of the differential equations. It's dependent upon, again, the approximation, the previous approximation from the first equation and the previous approximation from the second equation. So that's why we have to do this. We have to solve the approximation simultaneously because it's dependent. The first one's dependent upon the second one, and the second one's dependent upon the first one. So with this particular problem, how would this look? So our next approximation comes from the previous plus h times. Now here f, it represents the right-hand side of the differential equation, right? The right-hand side of this differential equation is y2 squared minus 2 times y1. So here we would have the previous approximation for the second function squared. So that would be the previous approximation for the second function squared minus 2 times the previous approximation for the first function. Okay. So this is specifically for our f. For the second equation, do the same kind of thinking. We do them side by side here. For the second equation, the next approximate value for the second equation would be the previous one for the second equation plus h times, this actually is f1, this f2, so this, the right-hand side of the second differential equation, evaluated at the previous t, previous approximation for the first function, previous approximation for the second function. So for this particular one, wi plus 2, I1 plus 2 is wi2 plus h times, now let's look at the right-hand side of this guy. So that was the previous approximation for the first, so this thing here, wi1 minus wi2 minus ti times wi plus, wi2 all squared. So let's start it. Let's do, we'll do one round of Euler's method for this guy and this guy simultaneously. Again, we're going to need this approximation in the next step. Okay. So we have W01. W01 is just the initial condition for the first equation, so that would be 0. We also have W02. The first approximation, the initial condition is 1 for this guy. Okay. So let's go through here. So next up is 1. So that will use W0, 1 plus 1/4 is our h times W0, 2 minus 2 times W0, 1. So let's see what that is. What's W0, 1? That's our initial condition for the first function, the first equation, plus 1/4, times, this is the initial condition for the second equation, which is 1, minus 2 times the initial condition for the first again. So that's going to be 1/4. Now, if we want to do, if we try to do the second iteration here, we're going to run into some trouble. Second iteration would be the previous from the first, plus 1/4 times W1, the second function, minus 2 W1 from the first function. So why is this problematic? Well, do we have W11? We do. It's a fourth, of course, H. Do we have W12? We do not. So that's why we need to solve simultaneously, because this is dependent upon the approximation from this guy here. So let's do that. W12, the first approximation from the second function, is W02 plus 1/4 times W01 minus W02 minus T0, Ti by the way, T0 times W02 squared. Let's plug in our values. What's W02? That's 1 plus 1/4 times W01, 0. W02 is 1. Minus, well, what's T0, right? So we haven't partitioned our T axis yet. So let's look at that. Let's come up here and do that. There's T. We know T is on 0 to 1. And the step size is a 4, so we're just going to count up. So that would be 0.25, 0.5, 0.75. So this is like T0, T1, T2, T3, T4. Okay. So be sure that you're using the appropriate T values in your algorithm here. So T0 is 0 times W02 squared, that's 1 squared. Okay. So let's see what we get. This will be 1 plus 1/4 times -1, 1 plus -1/4. It's 3/4. Okay. Separate these guys here. 9. Now we have the information needed for our second approximation for the first equation. So let's do that. So here we would have W11 is 1/4 plus 1/4 times W12 squared, that's 3/4 squared, minus 2 times W11, which was 1/4 again. So let's see what we get here. Getting 17/64 for this one. Okay. All right. Of course, we're going to need to calculate this guy. So this would be the second approximation for the second equation. So that would be W12 plus 1/4 times W11 minus W12 minus T1 W12 squared. It's always a good idea, especially because there's so many subscripts floating around here, just to bite the bullet and write all the notation out so we don't mess up. So W12 is 3/4 plus 1/4 times W11 was 1/4 minus W12 3/4 minus T1. T1 is 0.25 1/4 times W12 squared, that's 3/4 squared. Let's see what we get here. 151 over 256. Okay. Now, again, when do we know when to stop is depends on the problem that we have at hand, right? So in this case, notice that this side's dependent on t, so we have the approximation. When we do this first iteration, we have the known solution, our W0i's, W1i's, W2i, W3i, W4i, right? So we need to go to 4 iterations in order to get the solution at t equals 1. Okay, so keep that in mind. So just a couple more. W31 would be W21 plus 1/4 times W22 squared minus 2W21. So if you do the calculation here, let's see what we get. So plugging in these values into the calculator produces this number here. Okay? So W32. W32, what would that be? That would be W22 plus 1/4 W21 minus W22 minus T2 W22 squared. Let's see what we get when we plug in these values here. So W22 W22 is 151 over 256 plus 1/4 times W21, that is 17 over 64, minus W22, again 151 over 256, minus T2, T2 is 0.5, times W22 squared. So here we get 0.465296. So we know in order to get the, we have the approximation for W31 and W32. We need to do one more to get the solution at T1. Te is equal to 1. Let's do one more iteration of the algorithm. W41 would be W31 plus 1/4 W32 squared minus 2 W31. So calculating that, this gives approximately 0.164021. And then lastly here, W42 would be W32 plus a fourth, W31 minus W32 minus T3 times W32 squared. Calculating that gives 0.363328 approximately. So we have the solution using Euler's method for the system. So just be careful with this process. Make sure that you write out those subscripts for ease of calculation. The example also says check that the solution of the system are these two equations here, these two functions. So all we would need to do is just plug, make sure that the y prime of 1, so we take the derivative with respect to t of this guy, it's equal to y2 squared minus 2y1. So let's do that. So to check the solution, solutions. So we know that y prime 1 must equal y2 squared minus 2y1, right? Well, y1 it's told to us that it's te to the negative 2t. So y1 prime would be, well, careful here, it's a product of two functions of t. So derivative of the first, which is 1 times the second, plus the first times the derivative of the second. Derivative of e to the negative 2t utilizes chain rule. So same thing, times the derivative of that power, which is negative 2. Thus, our derivative here is e to the negative 2t minus 2t e to the negative 2t. All right. So let's check to see if this equation holds. So y prime 1 is this. Equal to our y2 squared, which is e to the negative t squared, minus 2 times this guy here, t e to the negative 2t. So when we raise a power to a power, we multiply them. So negative t times 2 is e to the negative 2t. And minus 2t e to the negative 2t. So you can see the left and right hand sides are equal. So this is a solution to y1 is the solution. We also need to check in y2, right? Y prime 2, we need to check this is also true. So in this case, we need to find y2 prime. So y2 is given as e to the negative t. So y2 prime is simply negative e to the negative t, utilizing chain rule. So let's check negative e to the negative t equals y1, which is 2te to the negative 2t, minus y2 e to the negative t, minus t times e to the negative t squared. So simplifying this will give negative t e to the negative 2t. These guys cancel. So that also checks out. Okay? Now, ordinary differential equations can also be used without being given a system. We can actually decompose a higher order ODE into smaller into a system of first order ODEs, right? So a higher order ODE just means that there are higher order derivatives in the equation, like a y double prime, or y triple prime, or y quadruple prime, whatever. So a degree n differential equation, or order n differential equation will involve some function of t, y, y prime, y double prime, all the way up to y, the n minus first derivative of the function y. We can actually decompose this by setting up some new variables. So for this particular problem, or this generalized problem, we would set y1 equal to y, y2 is equal to y prime, y3 is equal to y double prime, and so on and so forth until we get to yn equal to y, the n minus first derivative. So you can see that the subscript is always just one less derivative than what we're getting. So notice now that if we were to take the derivative of this guy, yn, so yn prime is the derivative of this guy, so that is equivalent to another derivative of n, the nth derivative, which is the original problem here. So here you can see that y is replaced by y1 here. Y prime is replaced by y2. Y double prime is replaced by y3. So on and so forth. So then all that we would need to do is solve the system of equations, just like we had just done. We can use Euler's method or trapezoid method, improved Euler, aka improved Euler. So let's convert the third order ODE below to a system of first order ODEs. So example 2. See how we convert a third order ODE into a system of first order ODEs. Okay? So we have a third order ODE. It's because it deals with the third derivative. It's equal to a times second derivative of y squared minus first derivative plus y times the second derivative plus this term involving t. Okay? So basically what we are going to do is, we know we can convert this to a system of three first order equations, differential equations. Okay? That is, we need y prime 1, y prime 2, and y prime 3. Okay. So the first thing we need to do is introduce some new variables. So we're going to let y1 be equal to y, y2 equal to y prime, y3 equal to y double prime. So, what would y prime of 1 be? So here, y prime 1 would be equal to y prime. Y prime 2 would be equal to y double prime, and y3 prime is equal to y triple prime. Okay. But notice here that this is not, these are not first order equations, right? These terms involve higher order derivatives. So what we want to do is revert these guys back in terms of y1, y2, and y3. So what is y prime equivalent to? y2. Y double prime is equivalent to y3. And y triple prime is equivalent to this guy here, right? This guy here. So that would be A times, well, what's y double prime equivalent to? y3 squared minus y prime is y2 plus y is y1 times y double prime is y3 plus sine t. Therefore, our system would be y1 prime equals y2, y2 prime equals y3, and y3 prime equals ay3 squared minus y2 plus y1 y3 plus sine t. So we've reduced it to a first order system that only involves these variables rather than the derivatives. And of course we could just do that Euler method on all three equations simultaneously. Of course that would be very tedious, so that's why the computer comes in handy when we try to do something like this. Okay? We can look at various applications, pretty interesting applications that involve this kind of thing. So let's start with the pendulum problem. Okay? I have given you the code for Euler's method for a system of two ordinary differential equations. I've also given you some code on Blackboard involving this application. It's like an animation of the pendulum problem and the subsequent one-body problem that we'll look at here in a few. All right, so let's consider this application. So a pendulum swinging under the influence of gravity that is unimpeded by friction of the air and with no force added to it can be modeled using Newton's second law of motion. And through some analysis of this equation with Newton's equation for force, the governing differential equation can be derived to be this. We won't go through the derivation of it. I'll just give you the formula there. So here, y double prime is equal to negative g over L times sine of y, where g is the acceleration due to gravity, which is constant. That's 9.81 meters per second squared. L represents the length of the pendulum's rod, and y is the angle made from the vertical measured in radians. So if you look at this figure here, we can see that the angle y is the angle made from the vertical with the pendulum rod, this angle here. The pendulum rod is of length L, and we have these forces, force of gravity versus the force, angular momentum of the pendulum bob here, okay? But that's neither here nor there. I've given you the code for that. So let's, for example 3, we want to convert this second order differential equation into a system of first order differential equations. So what we have just done. So example 3. So we know our differential equation second order is negative g over L sine of y. Okay. All right, so we know that this can be converted into a system of two first-order differential equations. So let's go ahead and do that. So again, we are going to look for y1 prime and y2 prime. what are these values? Okay, so we're going to let let y equal, y1 equal y, and y2 equal y prime. Okay. So y1 prime would be y prime, and y2 prime would be y double prime, which is the derivative here. So the derivative of this is equal to the second derivative of y. Okay. And now relating these terms back, y prime is equal to y2, and y double prime is equal to this quantity here. So that would be negative g over L times the sine of, well, what's y? Y is 1. Therefore, our system is y1 prime equals y2, and y2 prime equals negative g over L sine of y. So the solution of this system basically models the motion of this pendulum, right? So we're looking at the rate of change of the quantity y1 and y2, and this will represent the motion of the pendulum. So let's take a look at Matlab. We're going to apply Euler's method using Matlab to this, and we're going to look at how different changes in the parameter for step size, or h, how it changes our solution. Okay, so let's do that. All right, so here is the program. I've called it Euler 2. Euler 2. So what this does is it will solve the system of equations. It's done in a little bit of a different way. Here I'm nesting these functions. You don't really have to know how to do this. But basically, this is the top function is the function that will calculate the solution points. It will also plot the two functions, y1 and y2 versus t, on the same grid. The second function is just one step of Euler's method. So here you can see we're going to do one step of Euler's method, but since we're in this loop up here, it's going to do Euler's method however many times that we need it to. And then this last function is the differential equation. So here you can see I'm defining G and L to be 9.81, and we're going to assume length is 1 here. So you can see our two sides, our system of differential equations here and here, right? So our approximation Z1 is equal to Y2, and approximation for the second curve is given by our second equation there. Okay. So let's run this. I've also put in an example of the usage for Euler 2. Basically, Euler 2 takes on a time interval. So in this case, for example, if we wanted to look at the solution along the time interval 0 to 1, the vector of initial conditions, so this is the initial condition for y1, and this is the initial condition for y2. Excuse me. This is the initial condition for y1. This is the initial condition for y2. And then n represents the number of time steps, so however many steps we're decomposing this time interval into, okay, which can be calculated fairly easily. All right, so let's look at the solution for when 2, let's say we're going 0 to 10. Our initial condition is, what's that give us? So with the initial condition on y1 and y2, notice that here the solution y, again, is the angle between them, right? So y1 and y2 deal with that angle. So let's look at some initial conditions for y1. Let's say the angle starts at pi over 2. So if you recall, if this angle is pi over 2, that's 90 degrees. So it's 90 degrees out. So it should start sticking out straight to the right. And then the second initial condition is dealing with the force associated with the pendulum moving. So let's make that 0. And let's say h is 0.1. So if h is 0.1, how many steps would that be? Let's think. If h is 0.1, so our t interval, t is in 0 to 10, right? 0 to 10. And if h is 0.1, then how many steps would it take? Well, it would take 10 steps to get from 0 to 1, right? 0.1, 0.2, 0.3, 0.4. So here it would take 100 steps to get from 0 to 10. And we can get that simply by taking number of steps would be b minus a over h. Okay. So that would be 10 minus 0 over 0.1, which is 100. Okay. So let's try it out with 100 steps first. So you can see here that we are not getting a very good solution, right? Remember, this is a pendulum, so it should just swing back and forth, back and forth. In this case, we're seeing that the location of the pendulum, the angle, is kind of dwindling out. And this blue curve is the angle velocity. So how fast is this angle changing here? So this is not a very good solution when h is small. Let's try another one. Let's say h is 0.01, so we would have 10 times as many steps. That gives us a better indication. So the angle, here the blue curve is our angle. You can see that the angle starts at pi over 2, which is 1.57 or so, and then swings back and forth through 0 to negative pi over 2, and so forth. However, the angle, you can see some slight increase in that. So here, this is not a very good solution because we know that the pendulum shouldn't go past the pi over 2 angle, right? So here it's at 2.16, so the pendulum is swinging past its initial starting point. You can see that the angular velocity of this red curve is also kind of increasing. The amplitude is increasing each time as well. So with 1,000 time steps, or h equal to 0.01, this is also not a very good solution. Let's do one more. Let's make it, let's divide h by 10, so we add 10 times as many steps. Let me grab this. So this was the previous one. Now, at the increased time step, you can see that we get much more consistent results, right, over this time interval. The pendulum is swinging back and forth, reaching its original starting position. This was pointing to the right. Here would be pointing to the left, and so on and so forth. I've also given you a animation of this. It's called Pend. Okay. Pend. There's a lot of coding that goes into the animation, so I'm not going to make you do that yourself. This is given to you. Here we're using the trapezoidal step to get it, the trapezoidal method to do that. Here, this last function is the differential equation again. So that's dampened one. So here's our differential equation. Of course, if in the computer problems, what you're going to be doing is just manipulating these two expressions by adding or subtracting some dampening constant here. So you just have to rewrite this last line by adding or subtracting something. It's very simple. So let's look at that. So let's try. And again, the inputs for this are similar. Inputs for this are the time step, or the time interval, the initial conditions, and then the step size, okay? So let's look at what this thing's doing with 100 steps. Oops. This is the pend function, P-E-N-D. Okay, pretty cool animation. So you can see that it starts at its initial position was at pi over 2, and of course after it gets to the end, we see that. Here it's moving a little slower because it's taking more time to compute the solution here, which you can see. A bit of a better solution, right? So if we go back, keep your eye on that the bob of the pendulum. So here you can see it starts out going back and forth, gets horizontal, but as time increases, you can see what's happening to that angle. Notice the angle goes up slightly from the horizontal position, right? Which is not a great solution for this problem. With it being 1,000, you can see we get a bit of a better solution. Slower, more computation involved. You can see levels out horizontally. Again. But recall with the second one, we saw after several oscillations, it starts to get a little higher than horizontal. That angle was a little more than pi over 2 or negative pi over 2. So here the angle is negative pi over 2. be 0 at the vertical, and so on and so forth. As you can see here, maybe it'll do it this time. It's a bit above, and so on and so forth. So without wasting time, we can do the animation for our $10,000 steps. Of course, this one's going to move extremely slow because it's computing at a very small h, right? Very small h. But if you were to continue to watch this thing, it would not go very much past that equilibrium horizontal solution, okay? Which is what we should expect from the problem, theoretically. So here we saw for relatively large h, that was 0.1, we got a not so great solution because of the oscillation above the initial condition, right? It should not go past that initial condition. But lowering the h value gives a better solution, and that's good to know, right? The dampened pendulum is a little different, so you can see that the system of equations is just a little bit different. We've added, or actually subtracted, this term here, right? So what this dampened formula does is basically it accounts for the resistance of the air, right? The resistance of the air. So we should expect the pendulum not to just keep swinging back and forth, back and forth, back and forth forever and ever, but it should come to rest at the vertical, right? After a certain time, it's going to lose energy and come to rest at the vertical. Okay? So you have a computer problem that deals with that. Again, all you have to do is just change this line number 35 of this code, by just adding in that little expression. One last type of pendulum problem is force-damped pendulums. Basically, here, if you kind of consider like a magnetic field acting on the bob of the pendulum, then let's say an oscillating magnetic field that adds force to the pendulum as it swings. We just add this one term here. You have a computer problem for that as well. Okay, so you can look at that. You can do the animation and see what happens with that. Okay. Lastly is the one-body problem, which is pretty interesting. This one deals with orbital mechanics. So if we think about a planet orbiting its star or like a satellite revolving around the Earth, this differential equation models that situation. So we're going to think about the larger body, like the sun, positioned at the origin. And this differential equation, if solved, will identify the location of the planet orbiting the sun or the satellite orbiting the planet, either way, right? It can be decomposed into a system very easily like this. And I've given you the code for that as well. So let's try simulating with Euler's method and improved Euler's method this orbit problem. I've given you the orbit code in Blackboard. It's a lot of animations and things like that, so it's a bit tough to code for a novice. But basically here, this is going to be the solution for us. Here we're using the Euler method in the overall solution. Here I'm giving you the Euler step one step of Euler method. When we loop it, it'll calculate all the solutions for Euler method. You can also change this. If you change this to trap step, it will instead use this function to calculate the solutions for. Okay? And down here, you have the differential equation with all of the information plugged in, right? So if you look back at the differential equation, we would need G, which is 9.8, right? 9.81. We need the mass of the object, of the second object, the smaller object, and these location values here, okay? And some initial conditions. So let's look at what that looks like in Matlab. I've also, if you want to run this, I've given you an example of the implementation here. So this function needs a time interval. It needs a vector of initial conditions here, and in this order. So this is the x position, the initial x position, and the initial x velocity, the initial y position, and the initial y velocity. We need the number of steps per point plotted, and so it needs the number of steps and the number of points plotted, p. This is dealing with the animation, so no need for that. So let's just run this one here and see what we get. So this guy is going to simulate some planet orbiting around the sun. Our time interval is 0 to 100. Our initial x position is at 0, its velocity at 1, the initial y position is at 2, with velocity 0. We're going to make h, let's make this a little smaller first. Let's do 1,000. And then, let's see about this. All right, so you can see that with a small number of steps, relatively small number of steps, our solution is kind of crazy, right? So the planet does not stay in orbit around the sun, kind of just shoots off into space, right? So this is not a very good solution when h is very small. In this case, if we're going 0 to 100, and we're doing 1,000 steps, h would be equal to 0.1. Here, h is 0.1 if we go 0 to 100 with 1,000 steps. So let's decrease h to 0.01. Then we would need 100 divided by 0.01 steps, or 10,000 steps. So let's see if that gives us a better solution. Okay, so here is with h a little 10 times smaller. You can see that it's got a pretty good orbit. Let's see what happens after some time. So you can see the planet kind of outside of its original orbit, kind of spiraling out still, but slowly, right? So this is not a very good model, a very good solution, because the error is too large, right? It's because of the error, the Euler's method is just a order 1 method, the error associated here is going to be fairly large. So after some time, you'll see that it kind of just continues to spiral away from the sun. Okay. If we do an even smaller h, that's 0.001, requires 1 million steps. Of course, this is going to go fairly slow. So by the magic of video lecture, let's speed it up. So this is during its second revolution around the sun. You can see that Euler's method, it's going very slow, of course, because we have 1 million steps here, lots and lots of computations going on. But you can see that it's kind of thickening up this line, which indicates to us, stop it. Which indicates to us that this is even, it's a better solution, right? But you can see that it's spiraling out from its original trajectory. So a better solution to the problem, but the planet is still flying away from the sun, right? Which is not what it's supposed to do. So even, you can see even with a small h, Euler, because it's it's a low method, doesn't give us a very good solution. Let's try looking at the trapezoidal rule on the same problem. So here I can just change this to trap step. It'll use the second method. So let's go back to, save that. So let's rerun orbit with h equal to 0.1. So with h small, you can see that it's better than Euler, but it's still not very good. So if we up it to 10,000, remember Euler, for this one, Euler was kind of spinning outward. Here, let's see how trapezoidal method does. So a little slower because more computation, but you can see it the planet kind of just stays on its orbit around the sun. Right? It's not spiraling outward very much. That blue line is not thickening up, which indicates to us that it's pretty much staying the course around that larger body, right? So that's pretty interesting, how these differential equations can model some real life applications. Okay, so you should be able to do the last of the homework assignments. Here, exercise 1 and 2 deal with applying Euler's method to a problem, applying trapezoidal method to a problem, and then 3 deals with verifying some solutions. Computer problems 1, this deals with applying Euler's method. So I've given you Euler 2, so use Euler 2 on computer problem 1. Just make sure you put in the appropriate parameters. 3 and 4 deal with our pendulum problem. So you're basically dampening and force dampening a pendulum by adding the appropriate terms. Again, to do that, all you need to do is just add or subtract the appropriate values from the handout in this line of the code, in line 35. Okay?